Hello everyone. Today we will continue our discussion on trees. So next we will see a new definition: M-airy trees, especially rooted tree. Okay, let's see this definition. Rooted tree is called M-airy tree if every internal vertex has no more than M children. Then we call this tree M-airy tree. And we call this tree full M-airy tree if every internal vertex has exactly M children. Okay, so basically M-airy tree means how many children the internal vertex has. If not no more than M children, we call this M-airy tree. So maybe some internal nodes have 1, 2, 3, 4 to N numbers of children. So we call this M-airy tree. But if every internal vertex has exactly n children, we call this full M-airy tree. Because you can see this keyword is very intuitive. Full means it has at most the number of the children. Okay, so if every vertex has n children, we call this full M-airy tree. Based on this definition, we can accept the following trees. The following trees for M-airy tree for some positive integer n. So you can replace any different numbers with n. For example, if n is 2, then we call this binary tree because for each internal node, at most they have 2 children. Okay, and then you may have 3 array tree, 4 array tree, and so on. Okay, so let's see this example. For T1, we can see maybe we can mark internal vertex to check how many children each internal vertex has. Okay, so this is internal node, this one and this one. Okay, so the first internal node, it has 2 children, and then 2 children, 2 children. So if every internal node has exactly 2 children, then we call this binary tree, a full binary tree. Okay, next let's see T2. Okay, so for first internal node, 3 children, and for this one, 3 children, 3 children, 3 children. So we know T2 is 3 array tree. Has exactly 3 children, so it will be 4, 3 and 2. Next one, T3. For the first internal nodes, it has 1, 2, 3, 4, 5. And for the other 2 internal nodes, it also has 5 children. So we can see T3 is a full 5 array tree. Next for T4, we can see the first internal node has 2 children. So at most, the internal node has 3 children, but some internal nodes has 2 children. So we can see this is a 3-array tree, but not a full 3-array tree. Okay, next let's see another definition of M-array tree, complete M-array tree. if it is a full emery tree in which every leaf is at the same level, okay, so maybe we do we have the definition for the level of the tree? When we discuss the height of the tree, actually we are trying to convert from the roots to the leaves. And then along its paths, we define is the height of the tree. And then based on this paths, we can determine this is the level 0, level 1, 2, 3. Okay, so if we have every leaf at the same level, then we call this complete emery tree. Okay, so our first example, we can see all these nodes are the nodes 1, 2, 3, 4, 5, 6, 7, 8. These 8 nodes are leaf nodes. They are at the same level, level 0, 1, 2, 3. Okay, they are all at level 3. So this is a full binary tree because you can see for every internal vertex, it has exactly 2 children. And for every children, the leaf nodes at the same level. So this is a complete binary tree. Okay, next, let's see another counter examples. For this one, you can see they are full binary tree, but we have leaves at different levels. On these 4 leaves at level 3, and these 2 at level 2. So it is not complete binary tree. And of course, and lastly, let's see this one. All of these leaf nodes at the same level, level 3. But you can see for these nodes, it has only 1 children. Okay, so at least it is not a full binary tree. So if it is not a full binary tree, then it is not a complete binary tree. All right. Next, let's see another definition: older rooted tree. Okay, so an older rooted tree is an older tree where the children of each internal vertex are older. So we have a specific number or order for all these internal vertices. Then we can call this an ordered rooted tree. Okay, so how we define the order? Okay, actually we can for binary tree. Binary tree is an ordered rooted tree because we know each internal vertex has at most 2 children. And the internal vertex of a binary tree, we call them left child and right child. Once we have the internal vertex, it has 2 children. So we have left child and right child. This is how we determine the order. Because when we draw the binary tree, we can always give the order. This is the root, and then left child and right child. For this one, it also has left and right child. All right. Except for left and right child, we can also have the order for left subtrees and right subtrees. If we use left child as the root, then we can consider another rooted tree. So we call this left subtree. And of course, we also have right child, so we have right subtree. Okay, next, let's see this example. Consider the binary tree T. What are the left and right children of D? Okay, so let's discover where is the internal vertex D. Here it is. Okay, so the left and right children of D will be F and G. And what are the left and right subtrees of C? So C is here. So we know C has left and right children, H and I. If we consider H and I as the root of the rooted tree, then this will be the left subtree, and this will be the right subtree. Okay, so if you need to answer the question, then you can draw this one in this one is the left and right subtree. Alright, so you can see tree can be applied to many different applications. This is the structure of we have president, we have RDVP, marketing VP, and search VP. So it's the structure of the employee or members of a company. Then for VP, we have a research director or software director or hardware directors under the RDVP. So actually, this is the real structure of members in the company. So when you graduate and go to work at different companies, then you will see different titles, such as directors, VP, and CEO. Okay, so we can use the tree structure to present the organization of the members of a company. And we can also apply the tree structures for the directory of the computers. For example, if you use Linux system, then you will see we have the root directory, and then we have subdirectories under the root. For example, user or okay. Then for users, then maybe you will see other subdirectories. Then there will be another tree structures to present the directory of our computer. So you can see actually a tree can be applied to many different scenarios. Okay, next let's see some properties of trees. So this is a theorem. A tree with n vertices has n minus 1 edges. Okay, so maybe we can draw the tree by ourselves. For the binary tree, we have the root and left and right child. You see this tree has 3 vertices but 2 edges. So if you add 1 vertex, then you can see now we have 4 vertices and 3 edges. So in this case, you can see the theorem 2 is definitely right. Next, let's see how we prove by mathematical induction. So basic step, when n equals 1, that means we only have the root vertex and we don't have any other edges. Then by theorem, we have 0 edges. So it is correct. And then for inductive step, we assume every tree has k vertices and k minus 1 edges. And then we will see how to apply this inductive hypothesis to prove that for k plus 1 vertex, we have k edges. Okay, so remember, we need to apply inductive hypothesis and apply the truth to infer that k plus 1, p of k plus 1 is true. Okay, so now if we have a tree, so hopefully we have k, we assume k vertices and k minus 1 edges. So this is p of k. Then when we need to prove p of k plus 1, then that means we have 1 more vertex and the tree with k vertices. Okay, so maybe based on the original tree, we can add 1 edge and 1 vertex. So that makes this tree k plus 1 vertex. Okay, so if this is k plus 1 vertex, then how we apply inductive hypothesis? Because we need to apply this fact. Okay, so you can see, actually you can see, we remove 1 edges and remove this vertex to to make this k plus 1 vertex back to k. So in this case, we know if we have k vertices, then by our inductive hypothesis, we know we have k minus 1 edges. So the difference between this tree and this tree are because we remove 1 edges. So if compared to tree T and T prime, we can see actually if this one we have k minus 1 edges, then the tree T we will have k edges. Okay, so I think this proof is very easy. You can apply mathematical induction to prove this theorem. Okay, next one is also a theorem. A full emery tree with I internal vertex has n equals mi plus 1 vertex. N means the total number of vertices. So if we already know this tree has I internal vertex, how to infer the total vertex of this tree is n. Actually, n equals mi plus 1. Okay, maybe we can observe these trees firstly. So if we have I internal vertex, then how to infer the total number of the vertex of the tree? Okay, so the key is we know is emery tree, full emery tree. Full emery tree means for every internal vertex, it has exactly n children. Okay, so for this internal vertex, then we know it has 3 children. For this internal vertex, it has 3 children. For this one, it has 3 children. So if you times m and I, then actually you can mark this one, this one, this one, this one, this one, this one, and this one, this one, this one. Okay, but we have one vertex left. So the total number of the vertex of the emery tree is n equals mi plus 1. Okay, next let's see when we have different variables, then how we infer this equation. For example, in theorem 4, we have 4 emery tree with n vertices. Okay, so in our previous theorem, we know the variable m and I, and we try to infer what is n. But in this case, we know the given variable is emery tree with n vertices. Then what is I? Okay, this is very easy, right? Because based on the previous equation, we know n equals mi plus 1. Now we know the given variable is m and n. So what is I? Okay, I equals n minus 1 divided by n. If you need to represent I by the given variable m and n, then I can be write as m minus 1 divided by m. And what is the leaf node scale? Okay, so we know the total number n actually is equals to the internal vertex I plus the leaf node L. Okay, so given m and n, and we already know what is I. So L equals m minus I. And we need to replace I by the given variable m and n. So it will be n minus 1 divided by n. Okay, so that will be n minus n plus 1. Okay, so it will be n times n minus 1 plus 1. right? Okay, just a simple replacement of the known variables, then we can infer the others. In this case, we need to write I and L by the given variable M and N. So that will be theorem 4. Okay, next one, if we have full MRA tree with I internal vertex, so now the given variable is M and I. Okay, how we derive the total number N and the leaf node L? Right, so it's MRA tree with I internal vertex. Okay, so we know the total number N actually is Ni plus 1. Okay, so now the given variable is M and I. So we just represent N by these two given variables. So I think this is okay. Now what is L? Okay, so the number of leaf nodes actually is N equals internal vertex plus leaf nodes. And we know L equals N minus I, right? But N is not a given variable. Also, we need to rewrite N to Ni plus 1 minus I. So in this case, we just represent L by the variable M and I. So M and I are two given variables in this theorem. In this case, we'll have N minus 1 times I plus 1. Okay, so you can see this equation, you can just rewrite these equations to use known variables to represent unknown variables. Now I want you to write how to derive for full MRE tree, but we have L leaves, how to derive the representation by N and I. Okay, please write down your answer on the paper. And now we have two equations for N and I. So how to derive these two equations? If the given variable is MR3 and the L leaves, right? Did you finish your answer? Okay, please share your answer to the others. Okay, thank you. Okay, now we have our original equation. The total vertex n equals mi plus 1, and we know this is a memory tree. And we also know n equals the internal vertex plus the leaf vertex. Okay, now we can see we have the known variable n and l. Okay, so in this equation, we know n is known variables and l is known variables. And we need to calculate what is n and I. So by this equation, we can see they both represent n. So we can derive this equation. Mi plus 1 equals I plus L. Now in this equation, we only have mi and l. And m and l are known variables. So we need to calculate what is I. Right? So we can move all terms containing I to the same side. So we can leave 1 to the left-hand side and I to the right-hand side. So we can calculate I equals L minus 1 divided by N minus 1. Okay, now we know how to write I by the known variable M and L. And then we can use the representation of I into this equation. Because now we know what is I and L is a known variable. So n equals n minus 1, L minus 1 divided by n minus 1 plus L. Then we can get the solution. All right. So actually, I don't think you need to remember all these equations because once you know these two basic rules, what is the total number of n by full memory tree, and know the relationships of the internal vertex and leaf vertex will contribute to the total vertex n. And then you can rewrite this equation by any given variables. Okay. Or maybe in the final examination, you will see give a 5-array tree with 100 leaves. Then what are the total vertices n, and what are the number of internal vertices? So once I give you arbitrary number for all these 4 variables, then I hope you can calculate the answer. All right, let's see the definition of level and height. Okay, so now we have the definition for level and height. Okay, so let's see the height of a rooted tree is the maximum of the level of the vertex. So let's see what is the level. Level of a vertex V, the rooted tree, is the length of a unique path from the root to this vertex. Okay, so you need to calculate the length from the root to this vertex to discover this unique path, and then calculate the length of the path. That will be the level of a given vertex V. Okay, so take vertex B for example. So when we travel from the root to the vertex B, we can see this is the only unique path. And then this path, the length of this path is 1. So we consider the level of vertex B is level 1. In this graph, you can see actually B, J, K, these 3 vertices are at the same level, level 1. And then we have C, E, F, L in level 2. And for the roots A, we consider its level is level 0. So this is the definition of the level of a given vertex. And then when you calculate all levels of all vertices, you can discover what is the maximum of the levels of the vertex. And that will be the height of the rooted tree. So in this case, we have one vertex H, which level 4. That will be the maximum of the levels. So the height of the tree will be 4. All right, next let's see another definition of balanced emery tree. So a rooted emery tree of height h is balanced if all leaves are at levels h or h minus 1. Okay, so balance means this tree looks, we have left tree or right tree, right? So it looks, we have very similar amount of vertices at the same level. So it looks balanced. If we have the full definition, all this at level h or h minus 1, then we consider this is a balanced tree. So take T2 for example. We have this vertex at level 2 and this vertex at level 4. So you can consider this one is not that balanced because it's all of the leaf nodes at level h or h minus 1. But in this case, we have level 2, level 3, level 4. Okay, so T2 is not a balanced tree. All right, now we have a lot of definitions for tree. Currently, we have full tree, we have completed tree, we have balanced tree. I hope you can remember the definition of these trees. Then you can correctly determine what kind of the tree it is. So I want you to draw the tree of, if this tree is balanced tree, but not a full emery tree. So it is an emery tree, but not full emery tree, but it is a balanced tree. So draw the tree with minimal vertices and minimal edges. And what this tree looks like. Okay, let me repeat the question again. Draw the emery tree, which is not a full emery tree, but it is a balanced tree with minimal vertices and minimal edges. All right, one extra point. Do you want to try your answer on the blackboard? Okay, please. Okay, thank you. So let's see. We need to draw a binary tree. Okay, so which is not full binary tree, but it is a balanced tree. Okay, so let's see if this tree follows the definition of our question with minimal vertices and minimal edges. So is this a binary tree? Yes or no? So what's the definition of binary tree? For any internal vertex, it has at most 2 children. So that means you can have 1 children, 2 children, right? So in this case, the internal vertex has only 1 children. So it follows the definition of binary tree, right? So is this tree a full binary tree? It is not, right? Because for full binary tree, we need to have exactly 2 children for each internal vertex. In this case, the internal vertex only has one child. Okay, so it is not full binary tree. Is this a balanced tree? Let's see. For balanced tree, all leaves at level h or h minus 1. So in this case, it is. Okay, so very good. Okay, now I want to draw the tree which is not balanced, but this Emery tree is a full Emery tree, but it is not a balanced tree with minimal vertices and minimal edges. Just opposite requirement. It is full Emery tree, but not a balanced tree. One extra point, anyone? Okay. Okay, thank you. Let me go back to our previous question. So, because his answer is this one, right? So how about this one? Is this answer okay? It is okay, right? Mm. All right, but you have one extra point. Thank you. Okay, now our requirement becomes full binary tree, but it is an unbalanced full binary tree with minimal vertices and minimal edges. Okay, so let's see if it is a balanced tree. No, it is not, because we have the height of the tree, 0, 1, 2, 3. The height is 3. And we have leaves at different levels. So we have level 1, level 2, and level 3. So we don't have all leaves at level h or h minus 1. So this is not a balanced tree. So if it is a full binary tree, so for full binary tree, every internal vertex should have exactly 2 children. Okay, so let's see, we have internal vertex, this one, this one, this one. So they are all internal vertex with 2 children. Okay, so this one seems okay. So last question, can we reduce the number of vertices and edges? Can we? So how about we erase this vertex? No, we can't, because once this vertex is erased, then it's not a full binary tree. So we should keep this one. So how about we remove this one or these 2? Okay, if these 2 are removed, then this will be a balanced tree, right? So we cannot remove these 2. And we cannot remove this one either, because when this one is removed, then it is not a full binary tree. Okay, so probably this is the correct answer. Okay, very good. Okay, we have the last theorem, theorem 5. There are at most m to the power of h leaves in an Emery tree of height h. Okay, so if we already know the height of the tree is h, and there are at most m to the power of h leaves in this emery tree. Okay, so it's not that intuitive, but we can see how we prove the theorem by mathematical induction. If we consider the emery tree of height 1, then height 1 means we have the root. And then we have n, maybe at most n child. Okay, so if it's a emery tree of height 1, then it has no more than n children. So there are no more than n to the power of 1. Okay, so at most we will have n this. This is correct because we just have the emery tree, not full emery tree. So at most we will have n leaves, but we can have less than n leaves. 1, 2, 3, 4, 3, n. So basis step is okay. Next, let's see inductive step. Assume for all emery trees of height less than h is true. Okay, which means if we have the height of h minus 1, then at most we will have m to the power of h minus 1 leaves. We assume this is true. It will be our inductive hypothesis. Then next, let's see. Let T be the emery tree of height h. Then how to prove that we will have at most m to the power of h leaves. Okay. So remember, we need to apply the inductive hypothesis of the tree with height h minus 1 to the tree of height h. Okay, so maybe we can draw the tree like this. Okay, so this is our root, and this will be the children of the root. So we know it has at most n children, but we don't know how many here. But we know if we take this child as the root, and we have a subtree here. All right, so if the height of this tree is h, then the subtree of each one is h minus 1. Right? And we know the inductive hypothesis, it tells us we have at most n to the power of h minus 1 leaves at each subtree. Okay, so at most, how many leaves we will have in this case if we apply inductive hypothesis to get the fact for each subtree we will have n to the power of h minus 1. Then at most we will have n different subtrees. So the total possible leaves will be n to the power of h minus 1 times n. Okay, so at most we will have n to the power of h leaves. All right. So this is very easy if you consider we may have the subtrees of the height h minus 1, then we can apply the inductive hypothesis. At most, we will have m to the power of h minus 1 leaves. Okay, and then we can infer once we have n, at most n subtrees, then for the tree with the height h, then at most we will have m to the power of h leaves. Okay, so that will be the end of this section. Oh no, we have one more corollary. Okay. Okay, so based on the previous theorem, then we can derive the corollary. If we have a memory tree of height h, then it has L leaves. Then we can derive the inequality h is larger or equal to log L with the base m with the ceiling function. And if the memory tree is full and balanced, then h equals log L with the base m by the setting operation. Okay. So since it is a corollary, then we can see it must be very straightforward. We can derive these results from theorem 5. So theorem 5 tells us if we have a memory tree of height h, at most we will have m to the power of h leaves. Then we know the leaf number at most is n to the power of h. So the leaf number L will less than or equal to n to the power of h. And then we can take log operation on both sides. Okay, we take log and log here, and with the base of n. And in the left hand side, we will have log ml. In the right hand side, we will have log n to the power of h. So log n with the base n will be 1, and the power of h can be in front of this log. So it will be h. In this case, we will have the inequality h larger or equal to log L with this m. And we know h is the height, right? So the height is an integer. So log maybe is a real number. So if we constrain h to be equal, then actually it will be larger or equal to the ceiling of log L. Okay? So you can see this is very straightforward. If we take log at both sides, we can derive the results of corollary 1. Next, let's see if the memory tree is full and balanced. Okay, then we suppose the tree is balanced. Remember the definition of balanced tree. All leaves are at level h or h minus 1. Okay. So if we consider the memory tree of height h, then what is the least possible numbers of leaves? Okay, so we can see each leaf is at h or h minus 1 because we already know the height is h. So at least one leaf at level h. Okay, so maybe we can follow the tree. Okay, so if we consider the height of this tree is h, then all the leaves can at level h or h minus 1. Okay, so we should have at most at least one leaves at the level h. That makes this tree, we have the height h, right? So if we have no leaves on level h, then the tree will become a tree of height h minus 1. So at least we should have one leaves at this level. But you can see this is a full balanced tree. Okay, so it's a memory tree. So actually, at least we should have n leaves at the level h. But theoretically, we can see at least one at level h. Okay, and it follows we should have more than h and h minus 1 leaves. Okay, so this is our lower bound, right? So if we have a tree with the height h minus 1, then at most we will have this number of leaves. But now our height will be h, it will larger than this number. this will be our lower bound. Okay, so we can write L larger than n to the power of h minus 1 and smaller or equal to n to the power of h. Once we have this inequality, then we can log to this equation. So we will have once we take the log here with the base n, then we will have h minus 1 less than log L with the base n and less than h. Okay, then we can conclude if the log L with the base n is less than h and larger than h minus 1, then actually h equals log L with the same operation. Okay, so maybe this is a real example. If we have the height of the tree is 3, then we can see what are the possible leaf numbers we could have. So in this case, we have 6 leaves. Okay, so I just provide some possible trees with the height of 3. And maybe you can verify yourself how many possible leaves with the height 3 trees you have. Right? Any question about this section? Okay, so in this section, actually we have seen many definitions and a little bit properties about the trees. Okay, so in next section, we will see tree traversals. Okay, so firstly, we will see universal entrance system, and we will see different traversal algorithm, and we will see different notations. Based on this traversal algorithm, we can have what is called infix, prefix, and postfix notations. Okay, so we just introduced the definition of order the rooted tree and how to label the order of each vertex in the tree. So based on this, we can have the universal address system, just like this logic. Okay, for the root, we assign the label 0, and then for its children, we label from the left to right by 1, 2, 3, 4, 5. Okay, so we have level 0, level 1. And then for next level, we can use 1 as its prefix, and then we have first children, same thing as 3. So we have 1.1, 1.2, and 1.3. And for the subtree with the root 3, then the labeling system will have 3.1 and 3.2 for these 2 children from the root. Okay, so based on this, you can see when the level goes further, then we will have 3.1.1 or 3.1.2.1. Okay, so we call this universal entrance system. Next, let's see a different algorithm of tree traversal. Okay, so it will be the procedures for systematically visiting every vertex of an ordered tree, which is called traversal. Okay, so we have 3 common traversal algorithms: pre-order traversal, in-order, and post-order traversal. So basically, when we visit the tree or traverse the tree, we can consider the order of root and left subtree and right subtree. So you can see the name of this algorithm pre and post. Pre pre means we visit the root first. So you need to visit the root and then visit left and right tree subtrees. Okay, if we apply in order algorithm, that means the root is in the middle. You need to visit left subtree first and then root and right subtree. For post order, we know post means before or later. So that means we visit the root in the last position. So we visit left and right subtrees and then the roots. Let's see the traversal algorithm. Okay, the definition of pre-order traversal, if we have T as our ordered rooted tree with the root R, and then if we have only the root vertex, then the traversal will contain only R as our pre-order traversal results. Otherwise, if the roots has the number of subtrees, then we have T1, T2, Tn for our subtrees from left to right. So pre-order traversal begins with the root R and then continuous traverse the subtrees T1, T2 to Tn from left to right. Okay, so actually this is a recursive call of this traversal. So let's see a real example how we traverse the tree by pre-order traversal algorithm. Okay, remember pre-order means once we have root, left subtree, and right subtree, we need to visit the root first. So in this case, if we have the given trees here, okay, and the first node we need to visit is A. Okay, so okay, so now we can see the tree. We have the root A, and we have three subtrees by B, C, D. Okay, so now we have four candidates, A and subtree. So by pre-order traversal algorithm, we need to visit the root first. So the first output node will be A. And then we traverse left subtree and from left to right. So in this case, we have A and subtree B, C and subtree D. Okay, so now we output the root A. And then we travel the subtree by pre-order algorithm again. Okay, if we consider this is a tree rooted by B, then we will output B first because B is the root. Okay, and then left tree and right tree. So for the left tree, it's rooted by E, so we output E next. And then J, because J is the first subtree. And then we consider this subtree rooted by K. So by pre-order, we output the root first at K, and then N, O, P. Okay. Now we have output all these vertices of the left subtree of the rooted tree, rooted by B. Then we output F, because currently the root B and subtree E is already output. So the next one will be F. Okay. Once the subtree of B is output, then from left to right, next one will be C. Okay, so we output C. And then we have the rightmost subtrees, okay, rooted by D. So in this case, we output D first, and then from the subtree from left to right, so we output G, L, M, and then H, I. Okay, so if you consider this recursive call from the rooted tree, then you can apply apply this algorithm to all subtrees of the rooted tree. Okay, so in this case, let's see this sequence again. How we visit this tree by pre-order traversal. Okay, the first one is A, and then B, and then E, and K, and N, O, P, and then F, C, P, T, L, N, H, I. Follow the order root, left, right subtrees. Alright, so let's take this exercise by yourself to write the pre-order traversal results of this tree. What's your results? You have finished, right? So what's your answer? A, B, E, F, G, C. Okay, good. Okay, next one is in order traversal. Okay, so remember, in order traversal means we didn't visit root first. Instead, we visit the first subtree, first the left subtree first, and then we visit the root. And then by the sequence from left to right, we visit each subtree. Okay, so let's use the same example. So now we have the root A and we have three subtrees. So now we have four different components we need to visit. But by in order traversal, we need to visit the left subtree first, and then A, and then C, and then the subtree by B. Now when we need to visit the first left subtree, then we consider the root is B, then we have three different components. The first component is the left subtree by E, and then we have the root B, and then we have the root F. Okay, and then from the root A, and then to the resting subtrees, C and D. Okay, so now we have C. Let's consider the subtree rooted by B. For in order traversal, we need to travel left subtree first. Okay, so after C, we visit the subtree rooted by G, and then D, H, I. Right? So now we can apply this recursive algorithm again to the subtree with that. So for these subtrees, we need to do A, B, and then this subtree by K. Okay, then for this tree, actually we use N, K, O, P. And then for this subtree, we use L, G, K. Okay, then you will have a sequence of the visits by in order traversal. So let's see this example again. What's the results of in order traversal? All right, you want to try your answer? B, B, F, E, G, A, C. All right, very good. All right, our last algorithm, post-order traversal. Actually, we see the keyword post. That means we visit the root in the last position. And then we traverse from left subtree to right subtree by the order from left to right. we visit last time? Okay, so let's see. For the same example here, so we have four components: the root A, and the subtree rooted by B, and the root C, and the subtree rooted by D. We have these four components. But by post-order traversal, we need to visit the subtree B and C, and the subtree rooted by D, and then lastly the root A. And then we can apply this recursive call by this subtrees rooted by B. In this case, we need to visit this left-to-right subtree first. So we will visit this one, the subtree rooted by E, and then F, and then E. Okay. And then for this subtrees rooted by E, we need to visit J and the subtree rooted by K first, and then E. Okay, so if you decompose by different levels, then you can have a sequence of traversal results. Okay, so maybe just try the last example. What's the post-order traversal for the same tree? Okay. Wait a second. E, F, G, E, B, A, C, right? And A. Okay, very good. Okay, any question for this traversal algorithm? Okay, if no question, see you next week.